For the 25.2, the polarity of a molecule. We think about the rule of hydrogen chloride. It is a diatomic molecule. There are only one polar covalent bond in its molecule. As a result, we say that it is a polar molecule. Because the electrons is going to the chlorine side, the bonding electrons will be going to the chlorine side, will be attracted to the chlorine side. So this kind of arrow indicate the polar bond. That the indication means actually the bonding electrons is going to the chlorine side. You may think about like that way. Well, this also a bigger red value arrow, and then with the delta positive, delta negative, indicate the molecular polarity. That is where it is the delta positive, where is delta negative. So this is the key. If a molecule has more than one covalent bond, how can we decide whether it is a polar or not? Now, for hydrogen chloride, it's simple. It just has one covalent bond inside. As a result of that, it is not difficult to think about whether it is polar or not. However, if there is more than one bonding inside, we have to decide whether it is polar of the molecule is decided by the shape of molecules. The polarity of each bonding in the molecule. So for example, in water, molecules is in V shape. There is two polar bond because O has a higher electronegativity value than hydrogen, then they cannot cancel with each other. A water molecule we set it to be polar because they cannot cancel with each other due to its shape of molecule. The hydrogen will give the electrons to the oxygen. Hydrogen will give the electrons to the molecule, to the bonding electrons to the oxygen. As a result, the overall is going up. So the polarity, the bottom one is the delta positive, while the upper molecule is delta negative. So we may show it in an space filling model. As a result of that, if it is linear, the shape of molecule is linear, HF. So hydrogen gives electrons to the fluorine, and then the polarity, we show it molecular polarity will be like this way. Delta positive on the hydrogen side, delta negative will be on the fluorine side. Or if it is V-shape, as they cannot cancel, they are pushing the electrons up, and then the overall will be going up. So the hydrogen side will be delta positive, while the oxygen side will be delta negative. NH3, just the same. So as it is trigonopyramidal, while the hydrogen will push the electron, or nitrogen will attract the bonding electrons in that. So give the electron, push the electrons. While we say that the overall or the resultant force will be going up, the delta positive will be at the bottom side, that is the hydrogen, while the delta negative will go to the upper side, that is the nitrogen atom. So nitrogen atom bear the delta negative. Well, for this one, CHCl3, you can see that H has a lower value. It is 2.1 according to the Pauling scale, 2.1, while carbon is 2.4 or 2.5 something. So it will push the electron, or carbon will attract the bonding electrons to itself. However, chlorine has a higher electronegativity. It will draw the electrons towards itself. As a result, overall will be going down. So the electrons is drifting to the bottom of the molecules, just like this one, going down. And then at the chlorine side, then it's delta negative. At the upper side, that is the hydrogen one. Delta positive should be assigned to be the hydrogen atom. So that's the case. Nonpolar molecules. Molecules without polar bond are nonpolar. If the molecules, it doesn't bear any polar bonds, for example, hydrogen and hydrogen, they are identical. They don't have electronegativity difference. As a result, we say that they are nonpolar. But molecules with polar bonds can also be nonpolar. How can it be? If they are arranged in the systematically, or not arranged systematically order, we say that the polar bonds are arranged systematically, so they can cancel out with each other. For example, all the polarity of the polar bonds can cancel out with itself or with each other, then it is a non-polar molecule. But the point is, polar bonds should have equal polarity first. Equal polarity first. That is how. For example, the first thing, BF, this is BF, this is BF, is fulfill the first requirement. They have equal polarity. So bonding polarity is equal because they are still BF and BF, BF. While the second one, it is arranged, the molecules have arranged, the bonds are arranged systematically. Sorry, it is not systematically, it's symmetrically. So sorry. So the symmetrically means they cancel out the force with each other. They cancel the force with each other, then they have the arranged symmetrically. So sorry, again, and then they cancel out the force. So how can we say that? Now, this one is a super important point. The polarities of the three polar BF bonds cancel out each other. As a result, they are non-polar molecules. It is a non-polar molecule for BF3. Another case, which is carbon dioxide, CO2, like the first case is, the first scenario, they are having the same bond polarity. It is CO, and on the right-hand side, it is CO as well. So the first statement concerning about the bond polarities is valid, while another one is arranged symmetrically. The polarity of the bonds are arranged symmetrically. They cancel with each other. So the polarity of the two CO bonds or two polar CO bonds are cancelled each other. So we say that it is a non-polar molecule, just the same case as BF3 or CH4. They cancel with each other, or PCl5, although it is a very complicated one, but you can see that all the polar bonds can cancel out each other. Hence, it is a non-polar molecule. SF6 is octahedral. The shape of molecules affects the polar or not. Well, and remember, apart from the symmetrical or not, we have to consider whether the polar bond are the same or not. They are SF, SF, SF. So all of them are SF. So we can consider the second criteria, whether the polarity of the bonds or the bonds are arranged symmetrically or not. The polarity of covalent bonds and the shape of the molecule will affect the overall polarity of a molecule. So when we consider whether a molecule polar or not, so we have to think about whether there is at least one polar bond or not. If it doesn't bear any polar bonds, for example, hydrogen and hydrogen, they don't have any polar bond, or chlorine, then it is non-polar. So if, yes, it has one polar bond, at least one polar bond, how many? If it has one polar bond only, for example, it's just got one bond in here, H and then Cl, it must be polar. Another case, for example, carbon and then oxygen. So it is a little bit polar actually. So it is polar because it's just got one polar bond here. While if it is more than one polar bonds, whether they can cancel out with each other, if they can cancel out with each other. So how? For example, carbon dioxide. So they have two polar bonds. Yes, they have two polar bonds. However, the polarity of the polar bonds due to its shape can cancel out with each other. It is non-polar. Well, no, they cannot cancel with each other. For example, for this one, another case is given, is here. Oxygen has a higher electronegativity. Hydrogen is less. So the electrons overall, Now the polarity of the bond will be going here. As a result, the overall one will be going to the oxygen side. So we say that it is polar molecule. We have a term, like if you are interested, you may search about the term of about dipole moment later on. We will talk about this. We will not talk about this in the DIC level anymore, but you may think about the overall shifting of the electrons in general is the dipole moment. So this is delta negative going there, and then delta positive at the bottom side, that is the hydrogen one. So you may search about some information about the dipole moment. And for example, another example is oxygen is delta negative. So the overall one will be going down. So when we talk about this one, dipole moment, it is just like the overall shifting of the electrons, but it is not that case. But you may search about those information by yourself if you are really interested. But just let you know, because some of the time you will see the suggested answer in the past paper have the term dipole moment. This is just the overall. Take it simple, it should be treated as the overall shifting of the electrons going where, and then assigned to delta negative. But remember, it is the overall, but not particular the polar bond step. So we have to skip this slide. The shape and the bonding, that is here, going back. The shape and the polarity. Now here are some example or class practice you may refer. So let's take a look there later on.